Okay, here we go.
Okay, I don't know what that is. What is that?
All right. Yeah. Okay, polynomial. A polynomial is a type of function, family of functions. No, you don't. You don't need to write it down. You really don't. This is straight out of the book. You won't need to. You really won't need to.
Okay.
Polynomial is, this looks pretty ugly, but
Yes,
let's try to make sense of all this stuff. You will. You will. What this is saying, essentially, is that we've got a sum of terms. Here's one term. Remember that terms are things that are added or subtracted. So a polynomial is just a string of terms that are added or subtracted. Now, each of the terms is built in a very specific way, though. So here are 4 terms that show up. This is written generally. So the polynomials that we encounter in problems are going to have numbers in them instead of a's and n's. Okay? But this represents any possible combination of numbers. The first term here, this a part of each term, that's the coefficient. That's the number that's being multiplied by x. Each one of these terms, notice, has a coefficient, and then it has x to some power. Okay? The rules are, the coefficient of x in each of these terms could be any real number. It just can't have an I in it. But anything else is fair game. It could be a square root, it could be pi, it could be a fraction, it could be an integer, it could be a decimal. The powers of x are whole numbers, so they have to be positive integers, right, or 0. That's it. Otherwise, that's the only rules for a polynomial. All the terms in the polynomial are going to consist of real numbers times x to a whole number power. Okay, that's it. What is this kind of weird expression telling us then? It's just telling us that for this particular polynomial, the highest power of x is going to be n, which is an integer. Maybe it's 13, maybe it's 20, maybe it's 4. Who knows? This n that shows up attached to the a, that's called a subscript. It has nothing to do with the value of the number. It's just saying that whatever this number is out in front, that n just tells us that this is the number that gets attached to x to the n. Okay? Notice that these step down by 1 each time. If the first power of x is n, then the second power of x would have to be n minus 1. And then what does it mean when we see something like this? Plus, dot, 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 plus. What do you think it means? No. It's the same thing. Well, what if I were doing this? 1 plus 2 plus 3 plus dot, dot, dot plus 9.
It goes in order. It just fills in the gap.
Okay, following that pattern, etc., right? So following this pattern, right, eventually we're going to get down to powers of x that are small. And then eventually we'll get down to x to the 1, and then at the very end we'll get down to x to the 0. Anything to the 0 is what? 1. So we don't even write that 1. You don't write it because it's always 1, right? But as we walk down this thing, we're just going to step down the powers of x until we run out of powers of x, and that's a polynomial. Okay?
So we'll have to write out the whole thing.
No. So the ones we'll see will look normal. This is just this takes care of any conceivable polynomial. The ones we see will be specific. Okay. So what are the characteristics of this? Well, we say that the numbers in front of x are what we call coefficients. We know that, right? A coefficient is just a number that's multiplied by a variable. The leading coefficient is the coefficient of the biggest power of x. So a sub n, we could say. It'll be a number for us, though. We say that the degree of the polynomial is equal to the highest power of x. So that would be n in this case. If that were 7, if the highest power of x were x to the 7th, we'd call that a 7th degree polynomial. The constant term is the one that's multiplied by x to the 0, which doesn't even show up, right? So it's the constant, the number that's by itself. That's about it. Okay. Now we've seen some of these already. Oh, by the way, one other thing too. A polynomial is in standard form if we write it in decreasing order or descending order of power. So the biggest power of x first, next biggest power of x second, etc., all the way down. Okay, we've seen some of these before. Some of them we wouldn't even, we've never called them polynomials. They are. The first one, if the degree is 0, right? If the degree of the polynomial is 0, the highest power of x is 0, and that's just the constant. That's just one term by itself. You know, we would rarely think of that as being a polynomial. If we graph that, y equals a constant, it's just a horizontal line, right? Y equals 4 would be a horizontal line with a y-intercept of 4. Okay? A first degree polynomial. This is going to look familiar. We call that linear. And that would be f of x equals some number times x to the 1 plus some constant. Now, we've seen this. We spent a lot of time talking about this stuff. Instead of f of x, we typically called it y, same thing. And then, what was our most common formula for a line? Y equals mx plus b. Sure. So instead of calling it a sub 1, it had a real meaning for us. It was m. It was the slope of the line. And instead of being a sub 0, the constant in this case actually meant something. It was the y-intercept. But the whole time, we were just dealing with a linear polynomial, first degree polynomial, without knowing it. Okay? Then we went on and dealt with quadratic stuff. Well, that also was a polynomial. That was a second degree polynomial. Now, typically, we wrote that, instead of writing it as a sub 2x squared, we called that, in standard form, we called that ax squared plus bx plus c, right? But the a and the b and the c were just coefficients. And I had an x to the power of 2, an x to the power of 1, and an x to the power of 0. So that was nothing more than a quadratic polynomial. Yes, ma'am? I do, somewhere. Right here.
No.
Okay, so now how come, why is it then that we go to this, this a sub 2, a sub 1, a sub 0 stuff instead of a, b, and c? Well, what if we had a 37th degree polynomial? We'd run out of letters, right? A, B, C, we only have 26 letters, but we have an unlimited supply of subscripts. So instead we start to use these subscripts, right? The subscript matches the power of x. And then we can keep going with this. So that's where we left off last chapter. We could move on into third degree polynomial, we'll call it cubic. That's going to look like that. It's going to add this extra term. It's just a quadratic plus an x cubed term. And if we had another one after that, fourth degree, we'd call it quartic. And we could keep going. We really stopped naming them after that. But we could have as high a degree polynomial as you want. All right, so decide whether this is a polynomial. First of all, is it a polynomial?
Yes.
No. Okay, remember the criteria. What has to be true of the coefficients, the numbers in front of x? They have to be real. Yeah, no i's. That's it. Okay, what has to be true of the powers of x?
Must all be positive whole numbers.
Whole numbers. Good. Okay. So is it? Yeah, it is. It works, doesn't it? So what is the degree of that polynomial? Fourth degree. What's the leading coefficient? What's the leading coefficient? No. It looks like a half, but the leading coefficient is the coefficient of the biggest power of x. So, not 3. Negative 3. Okay, what's the constant? No. Negative 7. Yeah. Is it in standard form? No? But we could put it in standard form. Okay. So it is a polynomial. If we put it in standard form, we just have to put the biggest power of x first, not second. Okay? All right, so what about, we say it's quartic, right? Okay, so what about this guy? Is that a polynomial? I'm hearing a little both. Which one is it?
Yes, it is.
Okay. Are the coefficients of x, there's something weird there, isn't there? First term looks fine, but then that's not quite right, is it? That doesn't look like a term from a polynomial. A polynomial has to be a number times x, not 3 to the power of x. So that doesn't work. It's different. Okay? No go. What about that one?
No.
What's wrong with that one? Negative power of x. Can't have that. It has to be a whole number. No good. Okay? Not a whole number. Okay, last one. What about that guy?
No. Yes.
Yes, it is.
Yeah, it is.
It is. It is because it follows the rules. Each of the coefficients, including the constant, is a real number. It could be a square root. It could be pi. It just can't have an I in it. And then the only powers of x we see are whole numbers, so it's fine. Okay? All right, last thing I want to show you. So a polynomial is just a function. You know, they're a little bigger than what we're used to, but that's fine. One of the things that we want to do with any function we deal with is evaluate it. Okay, when we evaluate any function, value means number, right? So that means we're going to plug in a value for x and get back the value of the function, the value of y. This works the same with polynomials that it does with anything. I could, for example, if this is my polynomial, I could, if I want to know the value of f of x when x is 3, or f of 3 I could call that, I just plug 3 in for x and get an answer. But you notice that I've got some big powers of x there, and if x were a weird number, big number maybe, that would be kind of an awkward thing to have to calculate without using, say, a graphing calculator. Right? So there is a trick. There's a trick for doing this without having to plug x in to each of these terms and add them up. It's called synthetic substitution. And what it really is synthetic division, but we just don't know that yet. Later on, we're going to use the same process to divide polynomials. Here's how it works. Now, we've got to take the polynomial that we're going to evaluate. We need to, first of all, write out all of the coefficients, even the ones that are missing. So notice that we jump from x to the 4th down to x squared here, right? We skip x cubed. So what would the coefficient of x cubed be if it doesn't show up?
1.
No. What is it? Thought it said 0. Yeah. Because 0 times anything is 0. So we have to represent even the 0 coefficients that we normally wouldn't write because that term would just be 0 anyway. So we're going to write the polynomial in its entirety, including 0 coefficients. So there's our 0x cubed. All we care about in a synthetic process like this are just the coefficients. The reason we call this synthetic in math is we don't have to worry about the variables. We're only looking at the coefficients, which makes it an easy process. All we're doing is arithmetic here. We're not doing any exponentiation. We don't have to take things to powers. So we'll just pull down just the coefficients in descending order, all the coefficients, including the 0. When we do synthetic stuff on polynomials, we always create this bracket, this L-shaped bracket, to separate the answers from what we start with, from the numbers, right? And then whatever value of x we're going to plug into this, we're just going to stick out front. So we were plugging in the value 3 for x. Now, the way this works, we start the process going by just dropping down the first value of x, and as soon as it appears below the bracket, we know that we're supposed to multiply by 3 and then add that result, or multiply by 3 and put that number up here. So what is 3 times 2? 6. And then as soon as we get a number here, we always add in a synthetic process. We never subtract, we always add. So 0 plus 6 is 6. I get a new value of x there, so I multiply by 3 again. 3 times 6 is 18, and I add, etc. Okay? That's how it works. Now we'll go through that. Let's watch it happen. When we're all done, the book doesn't do this, and the PowerPoints don't do this, but they should. When we're all done, the very last answer we get, we want to put in a box. Okay? For now, think of the reason for it being in the box is because it's the answer. But later on, it's going to be the remainder when we do division. We always want to have a remainder box when we're done. So put that there. If we go through this whole process then, like we said, we multiplied 3 by the 2 and got a 6. 6 plus 0 is 6. 3 times 6, 18. Plus negative 8 is 10, right? Times 3 is 30. Plus 5, 35. Times 3. 105. Plus negative 7. 98, yeah. So that's our answer. So the value of the function, in other words, what we could say then is f of 3, the function evaluated at 3 is 98. Another way of thinking about that is a point that sits on this curve is the point x equals 3, y equals 98. Okay, those are all equally valid ways of thinking about that. That's the value of the function when x equals 3. Okay, make sense? All right, that's a good place to stop for today.